Okay, questions so far? So here we are rotating this, oops, sorry, lag here for me. Rotating this region around this axis. We sketched it out. We got our sample slice, and we have our formula for how that goes. This is true for any washer. Yeah, basically it's unbounded. It's not part of my original shape, right? My original shape is this region. So when I rotate it around, it carves out, but there's no part of it in the middle of the shape. So there's like a gap between my bounded area and the axis of rotation. That's what's going to create a hole in the thing, which gives me the washer. And yes, that you could also say it like that interior region here is unbounded. So that's not part of my region that I'm rotating. So what this really boils down to is whenever you have a disc or washer, you're going to use this formula. So really the only choices that you need to make here are what are R1 and R2 and what are the bounds. If I can fill those in, then I've got a definite integral and I can try and solve for that. So looking at my shape here, this bigger radius, the way to find a distance is just take the larger value minus the smaller value, but the larger value here is always 5 and the smaller value is 0. So this is just 5 minus 0, so that's going to be 5 squared. Right? This outer radius is consistent all the way through, but the inner radius changes. That's the inner radius. Just like before, right? That's the y value, and the y value there is the natural log of x. And then the bounds here are, I want to start with this left-hand side, which is 1, and go over to this right-hand side, which is 3. The bounds, I'm not totally sure. The bounds within the parentheses. This is the area of like the bigger disc, and then this is the area of the hole in the middle of the disc. So we're taking the bigger minus the hole, which is giving us the leftover bit of that washer. It turns out this integral is actually hard for us. We don't know how to integrate natural log of x squared. I'm not positive even offhand how I would do that, but this is the setup that we're looking for. Okay. So if I asked you to set one up like this, this is where I would be looking for you to stop. Other questions or thoughts about this one? Okay. Let's rotate y equals x cubed x equals 0, y equals 8 about the y-axis. So y equals x cubed looks like this. There's y equals 8, and there is x equals 0. So this is my region that I'm working with. I will warn you right now, for whatever reason, you know, these are sophisticated, complicated problems, but people make tons of errors just by graphing the lines wrong. So I'll write problem and say y equal 8, and people graph it at x equal 8, right? Or they'll mix up their horizontal and vertical lines or their axes. These kind of silly mistakes, for whatever reason, are extremely popular on these. So you've got to make sure you set the problem up properly in the beginning. So take your time, make sure you graph it properly. And we're rotating this one about the y-axis. So what I get then is this shape. Like a, I don't know, a solid bowl, right? A bowl with no hole in the middle, or a cup. Now, remember, if we want a disc or a washer, we have to slice perpendicular to the axis of rotation. Since it was rotated this way, in order to get my disc, I've got to slice it horizontally. The axis of rotation is vertical, so I need to slice it horizontal. And when you slice it horizontal, the thinness or thickness of it is not going to be dx, right? That's going to be dy. And this tells me all values need to be written in terms of y. This is a disk, so I don't need the whole part, right? It's just the integral of pi r squared dy. But because it's dy, both the bounds and the radius need to be written in terms of y. The radius is that distance, which is x, right? That's the distance from the y-axis out to here is x. But I need to change that x into y values. So here I would have to notice that x is the cube root of y. Do you see how I made that choice? This is really like the most important part of the problem, is understanding how to make these choices. I don't know that any of the choices are all that hard, but if you don't see it the right way, it's really hard to get them right? They just feel all confusing, and who knows which way to go. So I always focus first on whether it's going to be a dy or a dx problem. That informs everything else that I do. I also need the bounds. Again, those bounds need to be in terms of the y values. So I want to start down here at this y value, which is 0, and work my way all the way up to that y value, which is 8. All right, so you just want to imagine that's kind of like your slicer, right? I want to take all the slices starting at 0 all the way up to 8, right? And then this, we know the way this integral works, right? To calculate the precise value if I added them all together and let them get smaller and smaller. This one we could do, it's just y to the 2/3. So you could definitely find its antiderivative, but it's not that exciting. Okay, questions here? Okay. So let's take a look at what's called a cylindrical shell. And there's a kind of classic example here. Y equals x cubed minus 2x squared. Yeah. It's the other way around. Minus 2x squared minus x cubed. I think that works. Okay, so this function, we're going to rotate around the y-axis. And so this curve, we wouldn't know right away what this curve looks like, but it's something like this. And then I want to rotate it around the y-axis, which will give me roughly something like that. And it's maybe like a dog dish. Now, there's a little bit of a problem here. And the problem is, if we tried to do it the way we did the previous ones, there's our axis of rotation, right here. So to get a disc or a washer, in this case, I would have to slice it horizontally. Okay? It's okay. That would mean the thickness of that disc or washer is dy, which would mean everything has to get changed into y's. And here's where we run into a problem. This is very complicated to solve, to replace x with y. It's easy to replace y with x, right? That's what it tells me. But to figure out what x equals when you have a cubic function is sort of beyond our skill level, our algebraic skill level. So this is a problem. It's also a little bit of a problem because it's like the same function is kind of like the inside and the outside of this curve. It's like kind of not well defined clearly what part of the function is what. So what we need here is we need a different method, hence the cylindrical shells. So let's look at this again. And so what we're going to do here is we're going to, instead of slicing perpendicular to the axis of rotation, what I really want to do is I want to slice it vertical, like parallel to the axis of rotation, because if I do that, I'm going to get a dx. And dx is good in this case because I know how to change any y values into x values. I can put everything into x. But you can see if you just sliced it the way you did before, I think you can imagine that each slice would look radically different. It's like some would be solid, some would have holes in the middle. There would be no consistency to what those shapes look like. So instead, what we're going to do is we're going to take what's called a cylindrical shell. So I'm going to imagine I take a little kind of rectangle from my original area, and I see what happens as that rectangle gets rotated around. And what it does is it creates a cylinder. And if you looked at this from the top, what you would be looking at is a region like this. Okay. A cylinder, like a cookie, like you had two cookie cutters that were very similar diameter, right? And you punched them right through here. What you'd be left with would be this, which is called a cylindrical shell. And if I looked at all of these different shells, concentric circles, and I added up the volumes of all those shells, I would also get the volume, or an approximation for the volume of this shape. Okay. So what we need to do is figure out the volume of this cylindrical shell. And the way to see this is to really just, if you just cut it and rolled it out, you get pretty close to like a big slab. Call this thickness dx. This is the height, and this distance would be the circumference, which is 2 pi r. So the volume is 2 pi RH times dx. And just like before, I want to add all of those up from A to B. That is our formula for cylindrical shells. Now, just like washers, sometimes it will be dx and sometimes it will be dy. We need to figure out what the radius, the height, and the bounds need to be, right? If we can plug those all in, then we're going to have a definite integral, which we can then evaluate. Let's see if we can do that for this problem here. The radius, it turns out, of this, red shell, it's just the distance from here to here. It's x. And because my shell here is in terms of x, right, it's got a little thickness, dx. So it's in terms of x. The radius is exactly x. And that's true actually in general for cylindrical shells. The radius doesn't connect to the function, right? The function is really connecting a different curve than we're interested in. So the radius is just x. The height of this shell is right here. And the height is certainly just the y value, right? But it's on that curve, and we need that y value changed to x. So 2x squared minus x cubed. right? That's the y value. Questions so far? Okay, so the last piece is the bounds. And there's a little kind of change in thinking here with the bounds. If I want to add up all of these, so just, you know, this value is 2 and this value is -2. So there's a tendency to say I want to go all the way from -2 to 2. But remember, like at this x value, I'm getting this whole ring, this whole circle. So actually, as I start from the middle and move out to the edge, at each point, I'm getting each of these circles, right? And that's going to count every circle. So I don't actually want to go from -2 to 2. That would actually not give me what I want. I want to go from 0 to 2. So the bounds, another way of thinking about that, are the bounds cover the original shape. So remember, this part over here is actually like an artifact. It's not actually the curve. It's what happened when we rotated it around. So we're just really visualizing this part over here. It's not actually even on our function. So the only part that I would want to integrate over are my original bounded area, which is from 0 to 2. And it turns out that in the end, once we have this set up, this is not a particularly difficult integral. Pull out the 2 pi, I get 2x cubed minus x to the 4th. That's going to be x to the 4th over 4 times 2 minus x to the 5th over 5. When I put in 2 here, I get 32 over 4, so that's 8, minus 32 over 5. When I put in 0, I get 0. So whatever that is, 5 times 8 is 40, so 40 minus 32 is 8 fifths. It's 16 pi over 5. One thing I do know is that my answer needs to be positive, right? This is a volume, so it has to be a positive value. If I've got a negative here, I did something wrong. Possibly in the setup, possibly somewhere in the process, but something's not right if it's a negative. Okay. Questions on this? Yeah, that's a good question, David. There are a lot of smart people in the world, and I think people, people get very committed to solving certain problems. And I think that's actually where a lot of I mean, people are smart, but a lot of it just comes from sort of determination and kind of a new way of thinking or some insight into these things. And so, I don't know. I don't know the history of this part, right? Of where these came from or who sort of came up with this. But once, what I like about it is it's making us hopefully look at the definite integral in a different way, that it's like a tool that I can use. Now, maybe we aren't going to come up with the idea to break this into a cylindrical shell, right? But the idea is that that integral can help us kind of add up things that we might be interested in, right? And it turns out that a lot of things out there we would be interested in if we could do this. It's not just geometric things like volumes and areas, but it's lots of physical quantities too. I think the power output of a space shuttle, or you know, those are calculated by integrals, right, mathematically. So yeah, I mean, I don't know, maybe it's like reading a great novel, right? It's like we can appreciate the thinking and style and words, how they're put together. And it's amazing, you know, that we sort of get to benefit from that, right? And really this kind of fundamental theorem of calculus that connects these parts together, that is like a pinnacle of kind of human thought, right? It's like a great painting, or a symphony, or some you know, great novel or discovery. It's in that realm. So what I think it's pretty nice, that we can sort of see that idea. You know, if you went back a couple hundred years and had these ideas, you know, we're all sort of average mathematicians, right? But if we went back a couple hundred years with these ideas, we would be geniuses, right? No one would have thought or been able to look at these ideas in this way. So I don't know, you got me headed off in a different direction there, but it's a good question. And I think it's nice to think about it too, right? Sometimes, yeah, I just teach it, right? And I don't always, I understand it, but I wouldn't come up with it either, right? That's a different kind of thinking. Okay, let me show you one more here of these shells, and there are some kind of other complications that I will kind of cover on Thursday. Hopefully you'll have some questions too. One of the issues is sometimes our axis of rotation is not on the x-axis or the x-axis or the y-axis, and that makes it a little bit harder. But we'll get to that. So let's rotate. Y equals x squared. Let's go back to this original one we did. Y equals 0, x equals 2, but this time let's rotate it about the y-axis, and we're going to use shells. So it turns out that quite a few of the problems, you could actually use either method, the disc or washer or the shell. One's not always easier than the other, but like the last example we saw, there are situations where only one of the methods is really possible. So we do need to know both of the methods. A lot of people are more comfortable with the discs and the washers. But to be honest, the shells sometimes give us even easier integrals. Right, so this was our shape from before, but now I'm rotating around the y-axis. Right, which is giving us something different, right? It's the same shape, but when you rotate around a different axis, you're going to get a different volume and a different, you know, some different characteristics. So, in here. So here is our axis of rotation. And if I want to use shells, remember I need to slice parallel to the axis of rotation. Right? If I wanted a washer, I would slice perpendicular. For a shell, I slice the other way. That's really what's kind of nice about shells, is that we can, if one method is using dx, the other method will be dy. And that's why it's important for us. So for a shell, I sketch like a little slice, and then I imagine where that little slice would go as it rotates around. And that's the shell, my sort of sample shell or representative shell. Since it's a shell, I know it's going to be 2 pi RH. And this one, like the last one, the thickness here is dx. So everything needs to be x in this case. You can start with the bounds if you want. The x values go from 0 to 2. Might as well pull the 2 pi out in front. And then I need the radius. Just like before, right? The radius here is x. And the height. There's a y value there. And the y value can be rewritten as x squared. This is actually a nicer one to do with shells. If you do it with the disc or the washer method, well, you have to do the washers because you've got holes in the middle. So you have to do like one integral minus the other integral. It's not terrible, but it's a little extra work. Right? So that's another way that you can kind of help yourself out. 2 pi, the integral from 0 to 2 of x cubed dx. Again, we don't spend a lot of focus here on the integration part. Hopefully we've got that under control from chapter 5, right? We just want to make sure we can set these up properly. So it's really identifying, am I going to use a washer or a disc or a shell? Once I pick that, am I using dx or dy? Am I putting in the right formula for washers or for shells? And then how am I finding expressions for these parts? So you should know the formulas or write them down in your notes. And then it really just comes down to putting the right expressions into the right places. And, you know, there are little complications and it takes a little bit to figure that out. So you guys need to get started on this if you haven't already, so that you can start to figure out how to decide what to put where.